We now move on to the next part of our discussion on optical networks, which is access network or the last mile network. In the beginning of the module on network, I told you that the largest number of cable, the longest length of cable and the largest number of network equipments are actually getting deployed in access network these days, because the number of last mile users who are directly using optical communication is increasing day by day, because our bandwidth requirements are going high. So even to a single device, even to a single home, you require very high bandwidths, and optical fibers can provide very easily that bandwidth. So the access networks are typically called as the passive optical network or the fiber to the home networks. It connects the end users to the service providers. What are the requirements? It should be flexible in capacity, because in the sense that my bandwidth requirement may change as a function of time. In the night, for instance, offices may not require bandwidth, but homes require bandwidth. The signal format should be flexible. I should be able to adapt. The cost should be low, because the cost is directly going into the user, so the user should not be burdened with the cost of the technology. One thing that has happened over communication systems over the year is the bandwidth is increasing but the cost is decreasing, so you need to maintain that trend. And the maintenance has to be low, because if there is a requirement of frequent maintenance, it's going to be very difficult, because the number of users who are utilizing this access network are very high. So number of service personnel to maintain is going to be required to be very large. So these all should be done in a very low maintenance free model. So passive. So what is a passive optical network? It's also called as PON network. Okay. So it is a fiber access network. It does basically optical distribution. Okay. It just distributes the optical signal. So you know that the key element there is actually a star coupler or a passive optical splitter. Okay. And it enables the what is called as OLT. Sorry. Yeah. So it enables connectivity between what is called as OLT, the line terminal, and this line terminal is the central office of your service provider. Okay, so whoever is a service provider in your locality, they will have a central office. It's not like a big office or anything. It will be a shed where this equipment is kept protected, and from there you get connectivity to your individual user units, which is called as a ONU. So in an apartment complex, for instance, you could have the ONUs placed at the basement of your apartment, and the OLTs could be placed, if it's an apartment complex, the OLT could be placed in a central location in your apartment complex. Okay. Or if you're talking about a kind of slightly rural environment, your ONUs could be, the OLTs could be placed at the Gram Panchayat, or the place where multiple access is the place where you can have multiple access. And the ONUs could be placed in different points in a village. For instance, it could be in a post office, it could be in a bank, and from there the distribution happens. Okay. The typical transmission distances are 20 kilometer, right? Roughly, again, this is not a hard and fast rule, but roughly the transmission distance is 20 kilometer. One reason for this transmission distance is the allowed latency, the propagation delay. The propagation delay between the OLT and the ONU allowed is something like a few microseconds, and the distances, if you calculate corresponding to that, is less than about 20 to 25 kilometer. Anything less than that is also fine. So how did this access network historically evolve? The original communication network that came to a user. So historically, if you track, the communication network that typically came to the user was the telephone communication network. Okay, so telephone network. So they had very dedicated lines. For instance, you could have, this could be a subscriber which has a equipment which is kept by the telephone department in the home of a subscriber. I'm talking about landline telephone. And from there, data is sent to local exchange, and that is through dedicated copper cables. And the local exchange decides where the connectivity has to be made, and subscriber connection gets established through the exchange. So this is the, historically speaking, this is the first access network that got ever established. And later on, we moved from analog to digital. So it came digital, the cables came to be called as the DSLs or XDSLs. This is the family of technologies. The cables used were copper cables, and the technologies were called as the DSL technologies. There were several upgrades for this DSL technology, and this basically refers to all the digitized transmission between the different telephone lines. In fact, the first internet services were also established through these telephone lines, where you would actually dial into your local exchange, and the telephone exchange actually provided your internet connection. But that's all changed now. But still, the DSL services has standards that can give you 100 Mbps. From that, we moved on to optical fiber, where this connectivity now requires very high bandwidth, right? These DSL lines can give you only maximum of up to 100 Mbps, which is not sufficient for different enterprise users. So we moved on to distributing the information not in the electrical domain. We moved on to distributing information in the optical domain, and the optical distribution network came to be called as the passive optical network. Now, in a passive optical network, as I said, there is this OLT, and you have the ONUs, and so this is like a tree kind of a connection, or you can think of it as a star connection also, where there is a central node, and you have a direct fiber connection to different ONUs. So the ONUs are the user units, which are kept maybe in your apartment complex or maybe in the office building and so on, right? From the ONU, you could have multiple connections, which could be connected to your television, it could be connected to your computer, which could be connected to your Wi-Fi node and so on. Okay, so this is one simplest way of PON configuration. The other way of PON configuration is that suppose all these users are at a slightly far location. Then you could have a fiber linking the OLT, taking it through to the far distance. So this is something like probably a Gram Panchayat, and from there you go to the from there you move to a point where geographically move to a point where the users are, and just before you reach the users, you can split. A classic example is this is fiber to the curb, right? Fiber to the curb or fiber to the home, the OLT can from the central office of the service provider, it can reach, for instance, up to the specific apartment in an apartment complex through this fiber. And in that apartment complex, you could have the user equipments kept in different flats, right? And this split can happen at the apartment complex. So this split can happen in the individual building, and each of the ONUs kept in different flats can be serviced by the different legs of this passive splitter. Now, this is a configuration where multiple ONUs are using the services of one OLT, and here you are doing time division multiplexing to make use of the fiber bandwidth. So this is a TDM PON. You could also think of a situation where you can think of a WDM PON, where the OLT actually transmits all the colors lambda 1 to lambda n through the fiber, and then you can think of a WDM splitter like an arrayed waveguide grating, which will split out different colors, and each ONU will be serviced by a specific carrier frequency, which is what we are calling as a color, and then the bandwidth need not be shared in time division multiplex. It's like a wavelength division multiplexed bandwidth. And of course, from these ONUs you can now think of a tree topology, or you can think of a star topology which will service multiple sub-users, right? But in general, these are the three PON configurations. One is a direct fiber connection, TDM PON, or WDM PON. Going into a little bit more details of this connectivity, just to familiarize with the terminologies used. So you could have your personal computer or a TV or a telephone that can get connected to your ONUs and in the user side. So this will be in one apartment, this could be in another apartment. So each of them will have their ONT or ONUs, right? This is the same as the ONU that we saw here. These are the ONUs, and they can get serviced by the same optical splitter. And this is the central office of OLT. Is a central office, is the aggregation device which is managed by the service provider, and that can get further connected to the user facing edge. Now these edge routers are the points at which this add drop multiplexing happens in the metro network, and then it can just go on to the internet, or it could go on to the IPTV head and so on. Okay. The way a TDM PON works is the following. So from the OLT to the splitter, all the data that is supposed to be serviced for each of these ONUs are multiplexed in the time domain. So let's say user 1 requires a time frame, is serviced by in this time frame, user 2 is serviced here, user 3 is serviced here. Because the fiber can take a large data rate and the users do not really have equipments which can work at 10 Gbps kind of data rate, what you can do is you can multiplex the information that needs to be transported to each user in time, right? You can interleave them. The optical splitter is a passive device, so it just splits the information into n arms, in this case 3 arms, which means each ONU, the device that is kept at each user, actually receives all the information meant for all the other users, but each ONU is programmed to pick what is meant for its use. Okay, so that is contained in the header information. So in that sense, it is not a very secure way of communication, but this is a very practical way of communication. So every ONU selects the desired packets depending on the address within each frame, and the frame repetition rate, we would like to keep it with the SONET standard, SDH standard, and that is 125 microseconds. Right? Depending on whether you are doing SDH4 or 16 or 64, the data rate could be very different. And of course, the selection is based on the header address. The packet rate will depend on the dynamic demand of each user, the rate at which the packet is received. And this kind of scheduling is done in the MAC layer, which is a part of the layer 2. This is how the downstream traffic is handled. This is something like, we are trying to get the information, downloading the information from the internet. What happens to the upstream traffic? Let's say we want to send some information into your network. Then what happens is each ONU now acts independently. It is like a burst mode transmission. So the ONU knows that it has to transmit at a given rate. So it will keep sending information at, in this particular case, it's 1/3 rate, right? So it will keep sending that information. It will also keep sending a preamble information saying that, look, it will tell the OLT that, look, I'm going to send the information now, and then it starts sending the information. Each of these ONUs will do the same. The OLT is the one which actually synchronizes all these three, and it forms this complete packet, and this packet is what will get sent to the edge router of a metro network. Okay. So, the time gap, so it's not that even though we say there is this is 1, 2 and 3, there is a time gap given between 1, 2 and 3, so that any synchronization or any kind of delays can be accounted for. Again, the scheduling is done by the MAC layer. Initially, when you are trying to set up the system, the OLTs also have ranging facilities. It means that it can find out, it's not necessary that all the users are situated at the same physical distance. The ONUs could be located at different physical geographical distances. So, the time taken by each of these packets to reach may be different. So, when this guy does the timing synchronization, it should exactly know what's the distance traveled by each of these packets, so that it can align in terms of time. So, for that there is something called as ONU ranging that is done by the OLT, which keeps doing it once in a while, so that the timing synchronization is maintained. Okay. So, this is how the upstream TDM PON works. Now, there are 3 standards that are evolved for this TDM PON. Traditionally, it was called as the A PON and B PON, and this is the asynchronous PON and type B asynchronous PON, which was running at a slightly higher data rate. And these days, what gets installed is what is called as a gigabit PON, and the alternate technology is EPON, Ethernet PON. Okay. So, the difference is in how this framing is done. In terms of data rate, APON, BPON handles 155 or 622 Mbps, whereas GPON is roughly 1.25 Gbps, or it can handle 2.5 Gbps, whereas EPON is about 1 Gbps. The upstream data rate is any of these. Because of this interoperability requirement, the GPON and EPON should also, or essentially all this data rates should be multiples of each other. The upstream data rate is, in case of EPON, it is kind of symmetric, both are 1 Gbps. The downstream and upstream data rates are slightly different in GPON. Because of the philosophy that you may not be sending too much of information. A classic example is internet data. You may not be sending too much of information, you may be downloading more than what you are uploading. So, your upstream data rate is about, it can support much lower data rates, whereas downstream is always gigabit PON. Different encapsulation methods are used, and the most interesting thing is that the time that is allowed for laser on and off, for the automatic gain control of the laser and the carrier and data recovery. These are the different processes we had talked about when we talked about transmitters. The time taken for that, the guard time for all that is 154 nanoseconds, because the data rates are very small in this, whereas in GPON it is only 444 nanoseconds, whereas in EPON it is 400 nanoseconds. So, what is this timing? So, initially the laser could turn on, the time taken for the laser to turn on, you are giving some guard time for that. There is a time interval given for which you are adjusting the gain of the electrical front end amplifier. You want to make sure that the gain is such that the signal power is constant. So, there is a time taken for the front end electronic amplifiers to adjust the gain. So, that is the AGC time. This is the time taken for the carrier and data recovery, and then also and then is where your actual data comes in, right. So, the inter ONU guard time. So, this was the packet from 1, this is the packet from the ONU 2. The inter ONU guard time is the largest in EPON. It's very strict in case of GPON. So, the way they are doing is the laser on off time is supposed to be only very less in case of GPON. So, it means that the way you implement GPON, the hardware required to implement GPON is going to be much faster, and that makes it a little more expensive also. So A PON and B PON as were the first standardization. It supports the legacy telephone network, it supports the legacy access network, whereas B PON is the broadband PON. It had supported a slightly larger data rates. GPON is a standard given by ITU, the International Telecommunication Union, whereas the EPON is the standardization done by IEEE. So these are different standardizing bodies. They are coming up with their own standards, but the key is that they are all interoperable. So this is how the different architectures of PON will look like. Typically, you have 10 to 20 kilometers. It could support APON, ATM PON, or EPON or GPON. The splitter numbers are typically 1/16 or 1/8 or twice. It could be either 1/4 further split to 1/8. The typical wavelengths used are 1550 nanometer for the broadcast, which is like a cable television, for instance, that is 1550 nanometer. 1490 nanometer is used for downstream data, and 1310 nanometer is what is used for upstream data. So which means that there is no contention in terms of wavelength. If it is not used for video transmission, you could use data also for 1550 nanometer. There is also an evolving technology called as extended reach PON, where you are trying to increase the distance. This is specifically for sparsely populated areas, or where your the access network to the central office is slightly longer. So you can go all the way up to 70 kilometers with the fiber, and because it is 70 kilometers, there is a significant fiber attenuation. So here you could have EDFA, or you have regenerators, and then further it gets split. So there is a processing stage here with power amplifier. So this is called as an extended reach PON, and there are these active nodes here in extended reach PON, and from there the access happens like earlier. So that is up to 10 to 20 kilometers. And as we said earlier, in WDM PON is a scenario that is currently emerging standard, and I think the standards for WDM PON are already out. This is a case where each optical network unit, ONU, requires a large data rate. Okay, so this is a fiber to the building, and within that there is a large number of users, so you cannot time division multiplex with other users. So what you do is you take a dedicated wavelength for your own building, and similarly you could have another color servicing an ONU which could service multiple buildings, or if depending on the usage, it is a large usage building, depending on how much is the usage, you can actually have dedicated colors for each user, right? So here you have the benefit of further doing TDM PON here, and you could also do WDM PON. So what is emerging is a hybrid TDM WDM PON, where you could have downstream and upstream traffic which has multiple colors, and then there could be a arrayed waveguide grating router which splits the different colors, and then you have a passive splitter which will split it into multiple users. So your TDM happens here, and then you can also have the WDM. So this is kind of making use of both the TDM and WDM. What are the design considerations when you try to decide what kind of passive optical network that you want to do? You want to see how many homes you want to connect, which means that decides the number of split ratio. And you know that when you split by 1/2, there is a 3 dB loss, right? So you can calculate the split loss, the splitter loss, by 2 raised to n. So minus 10 log of 2 raised to n. This will give you the split loss. And the more the number of users, the more is the split loss, which means the more should be your transmit power, which means that there is a limit on the number of users that can be serviced. So one of the key design considerations is the number of users that decides the split ratio. You cannot arbitrarily increase the transmit power to service all the users simply because of the nonlinear effects in fibers we have said. So you cannot increase the power arbitrarily above 0 dBm, and so the number of users that can be serviced will get limited. How well can you share the channel in terms of TDM and WDM? What is the quality of service that is required? What is the data requirement? So, for example, HDTV is about 20 to 25 Mbps requirement. Pictures can be run at 1 MB compressed. Audio streaming would require 380 kilobits per second. So, in a house, it depends on, how many HDTV channels are you viewing simultaneously, how many audio are you downloading simultaneously. You can get an estimate of what is the peak data rate required for a given user and the number of users in that scenario, and then decide what should be your split strategy.